Hi everyone, welcome to our video on partial derivatives. So partial derivatives are very similar to doing derivatives, but we have multiple variables, and when we do a partial derivative, we just treat one of the variables as a variable and the rest of the variables as a constant, so just like any regular number. Okay, and with that, let's read through this. So partial derivatives are helpful in finding a rate of change when more than two variables are involved. The partial derivative of f with respect to x is the derivative of f obtained by treating x as a variable and y as a constant. The partial derivative of f with respect to y is the derivative of f obtained by treating y as a variable and x as a constant. We usually, since we have x and y being part of one side of the equation, we usually let z be the other. So z equals some xy expression is what that's kind of staying right there. So z equals some xy expression. And the notation that we have for it, so the partial derivative of f with respect to x is this little notation where we do a little tiny x down below. So notice there's no prime. We just put a little x. Or we use this, which is del f del x is how that one would be said. This one is the more common one that we use, but the second one is also just fine. And then the partial derivative of f with respect to y is this notation, or the other one right there with df dy. So notice we just put a little y symbol down there to show we're doing the derivative with respect to y. Okay, and again, the partial derivative is very much like just doing a regular derivative, so all those other rules are still there, like the power rule and the chain rule. But if there's a product or quotient, it does have to be a product of quotient or multivariable functions, such as like this one right here, because this has both x and y, and then it's also timesing something that has x and y. So this would require the product rule if we're doing a derivative of it with respect to x or respect to y, because both have x and y multiplying it. Whereas like this one, in example 1, we don't do the product rule here, because it's not multivariable times a multivariable, it is just x times y. Okay, so anyway, so we'll get down to this parenthesis type 1 in a little bit. All right, so I'm going to do these ones in blue. So let's find this first. So this means we're doing it with respect to x. So we have this function with respect to x is what we're doing our derivative to. Okay, and so let's break it down. So we do f little x, x comma y, equals, okay, so the derivative of 3x squared with respect to x is 6x. So that's just like normal. And then we have plus, all right, the 5 is still just hanging out just like it always would. That is a constant. The derivative of x is 1. And then this y cubed is treated like a constant, just like this 5. Just how I wrote 5 down, I'm just going to write y cubed down. And then that's it. And then we'll just simplify. So we have f little x, x comma y. So this is the partial derivative of f with respect to x is equal to 6x plus 5y cubed. All right, done. All right, and then let's do the other one. I'm going to use green for the y for these problems. So it's still this function right here that I'm looking at, and I'm just going to set it up. Here's our partial derivative with respect to y. Now the first term is an x term. So, and that is treated like a constant. So if x is treated like a constant, then the derivative of a constant is 0. So I'm going to use a placeholder there. So the derivative of an x term, if we're doing it with respect to y, is 0. Because again, that's treated just like a regular old constant. And then we have plus 5. Now the x is treated like a constant. So I'm going to do exactly what I just did with the 5. I'm just going to copy it and paste it just like that, 5x. And then now the derivative of y cubed would be 3y squared. And then we just simplify, so f little y, x comma y equals, well, I don't need the 0 anymore. And then from here, I could do the 5 times the 3 to get 15. And then x y squared would be just attached. That's it. Okay, so I think they always look a little worse than maybe they really are. Okay, so it is just the main hurdle to this is just kind of ignoring one variable, just kind of making it tag along is really what all it's doing. Okay, so let's try this one. So let's let z equal this expression, and then find del z del x. So that means the derivative of z with respect to x. and this is the partial derivative of z with respect to y. Okay, so let's do I'm going to use my colors again, so let's this one in blue. Okay, so I've got my function here. Well, it looks like it's a chain rule problem, so I'm going to set I'm going to do u equal that whole power. So I have 10x minus 3x squared y cubed plus 5y. And then that way, let's rewrite it. So let's just put it down below real quick. So give a little space since I'm going to do this all vertical. So yeah, that should be good. So z equals, so I'm saying this whole thing is u. So I have 4e to the u. So we use the chain rule just like normal. Okay, and then with this, to do this derivative, so I'm doing it with respect to x. With respect to x. Well, let's use the same notation for partial derivative. So I'm going to do u with a little x, and then now let's go through it. Okay, so the derivative of 10x would be 10. The derivative of the second term, well, this minus 3 would just be there. The derivative of x squared would be 2x. The derivative of, well, not the derivative, y cubed is treated like a constant, so that means just attach it, just like I did with the 3. So y cubed is just attached. And then plus 5y, well, if this is treated like a constant, then this would be 0. The derivative would be 0, because it's with respect to x still. Okay, and then really just one thing of cleanup. So u little x equals 10. This looks like it would become minus 6xy cubed. Okay, so there's u little x. I'm going to cloud it like that. All right, and then now let's go back and do our derivative here, our partial derivative of z with respect to x. So we would do del z del x. So it looks like a d is just a little bit more curvy. Equals, well, it would be 4e to the u. So it's the same thing. So it's the same rule. The derivative of an exponential is itself. So I copied and pasted it, but then times by the derivative, the partial derivative of what we're looking at, which would be u little x. Okay, so instead of like du attached to the side or du dx, it's u little x. And then now it's just copy and paste all of those in, and we have it. So we have del z del x is 4e to the u, which is that whole thing there, the 10x minus 3x squared y cubed plus 5y times u partial derivative of u with respect to x, which I clouded, which is the 10 minus 6xy cubed. So that would just multiply it, and you could rearrange things if needed. I'm going to skip that step. I think this is fine, and that's our partial derivative. Okay, so that's that. And then let's do the second one here. Well, it's pretty much the same setup where I need my u, which again would be the whole power, 10x minus 3x squared y cubed plus 5y. And then let's do its derivative with respect to y. So this first term is treated like a constant, so that means its derivative is 0. And then we have minus 3x squared is treated like a constant. And now the derivative of y cubed would be 3y squared. And then plus the derivative of 5y would be 5, because it's with respect to y. Okay, and then just like the first one in blue, well, this could be cleaned up a little bit. Let's make that looks like a y, so let's change that. So it's the partial derivative of u with respect to y is, this looks like it becomes negative 9x squared y squared plus 5. Okay, so there's our partial derivative. And then now let's go ahead and rewrite our z, so it's in terms of that u. So it is z equals 4e to the u again. So I wanted to use a u sub. And then, well, the derivative of this with respect to y would be written as del z del y, which is equal to, again, exponential function is itself as its derivative, so 4e to the u, but then times by the partial derivative of u with respect to y. And then again, we have all that, we just have to plug it all in, and then we're done. So del z del y is 4e to the whole power thing there, the 10x minus 3x squared y cubed plus 5y, and then times our clouded partial derivative of u with respect to y, so negative 9x squared y squared plus 5. And again, that's probably fine. If needed, we could rearrange, but I'm going to leave it just like that. Okay, so there's a couple example problems doing these types of problems. So again, partial derivatives, just that one variable is the focus. The other one's just kind of coming along. It's just attached. It's just tagging along there. Okay, but that's it for now. Let's take a break. We'll do a couple of other variations in the next video. But for now, that's it. So thanks for watching, and I'll see you again soon.